Okay, good afternoon everyone and welcome to my talk about minimal logging. I'm thankful for the organizers to let me open this B track here on Meeting C++ 2023 with my presentation. So my name is Koen and I'm from Belgium and I'm currently working for the Van de Wielen group. And this may be a name that is not too familiar to you, but we're a textile machine manufacturer from Belgium, which started as just a family company for weaving machines, but now has grown to a very big company which has all kind of textile machines. So that's why we call it like that. So I'm leading a team working on embedded software there, so to make sure that the operator can choose the carpet which he wants to make. And if you're lucky, or if we have done our work correctly, this is an example of a weaving machine. Then you start off with like almost 40,000 bobbins of yarn. And then at the end, with the jacquards here on top that produce all the complex patterns, you end up with a carpet. And actually, there's a fairly decent chance that the carpet we have our feet on now is actually produced on one of our machines. So that is quite nice to note. Before that, I worked at Nikon Metrology, which is a company that makes measurement software. And I like to mention it here because also some of the ideas that I will present originated there. Some more background, perhaps. I studied mathematical engineering. And if I'm looking back, I can see that my first contact with C++ was in 2003, where I did an implementation of the discrete Fourier transform. But for understandable reasons, I'm not going to show that code here today. No, instead I want to focus on logging and then some of the adventures I had with that. So just to set things clear, some examples of typical log statements. Our code base uses Qt. So there you can have this kind of statement where you have a... that has some delay. Where you have some primitives like debug and warning and so on, where you can stream some data to. And the nice thing is that this automatically adds a new line at the end, so your code is not riddled with new lines or std end lines or whatever. And also, these streaming operators make it really convenient to use it with all the types that are present in Qt. It adds quotes to strings, it adds the spacing where necessary. There's some decoration for the typical types and so on. So it's really easy for a developer to write these log statements. There's also the possibility to log or to categorize your logging. So you can define different categories of logging, and at startup, you can even choose which ones are active and which ones aren't. That's really useful because by default, you can put most of them off. And if you realize there's an issue at the customer, specifically on that machine, you can turn on specific extra debugging logging or something similar. Also for the output, there's a plethora of options to format this. You can add the file, the line, the method, of course the timestamp and so on. So that's really quite flexible and easy to use. But even if you're not using Qt or any other framework with the standard template library, you already have enough to do it. So you can, for example, define here a log macro and use the same formatting options which you have, or similar formatting options to also create a nice output. To include the line function and so on, you can use the preprocessor macros, of course, and also end up with an output that is fairly similar. But with C++ 20, there's now the source location feature where you can write this without a macro and actually use this trick or this common pattern where you have a function which takes an additional optional argument which you default to std source location current, which then once you do the logging at the bottom gets instantiated at that location. Note that this requires compiler support because, well, I wouldn't know how to write this function, and that's something you really need the compiler's help in to get this up and running. So some examples of log statements. Actually, when I was investigating some timing issue on a machine, I noticed that if I added one extra log statement, the entire behavior changed. So I had some kind of timing issue, and it went completely away when I added one more logging statement. So that was really surprising, to me at least, at that point in time. So I went and started investigating what is the impact of this logging. So looking at just a generic case of logging a boolean, an integer, and a floating point, I ended up with a measurement of queued being this amount of time and stdio stream taking that amount of time. So at first you might think, okay, Qt is faster, we should surely use Qt for that, but that's only the average. We have to do some more statistics on that. And if we look at the error bounds, then you can clearly see that although the IO stream solution is a bit slower, it is much more repeatable. So it's using this method, it will create a more predictable overhead to your log statements. So that's the reason why you always need to do some statistics on there to make sure that well, you get something that is repeatable. That's a lesson I learned from the metrology side, of course. I intentionally did not put any numbers here, but to put it into context, let's look at what it takes to query the current time. So that's an operation any log has to do to be able to print out when this happened. And then you see that this is quite a big difference. So in an ideal case, you would prefer to end up somewhere more to the left instead of these quite large results. So what else is at play here? What else is causing this large discrepancy between these two measurements? And well, I think there are three sources of overhead. One being formatting. So printing out or converting data types to strings is really something that can take up some time. And also log files notoriously are very verbose. Having thousands of machines in the field at customer sites that all produce log files. If you have to analyze an issue and go through tons of those log files, it's really, you notice how much suboptimal things are logged, things that are not necessary or repeated too many times. So there's log files are quite non-ideal in that sense. And also because so much is logged, I think it puts additional strain on the memory system, which can also cause some of the slowdowns and might even slow down your software itself. So adding some log statements into a hot loop somewhere might really mess up your performance. This is also confirmed by a developers conference presentation of 2016, where some Apple engineers talked about this and proposed a different solution. But so I really want to reduce the amount of overhead, and the actual spoiler here, the blue bar, is the performance of what I'm going to present here. So that should be interesting, I hope. So minimal logging. I previously gave this talk in a users group meeting where I went into used live coding to present the entire framework. Or well, framework is a large name or a large term because the resulting code only is 200 lines. So that's really feasible for a live coding. But as I feel that I can present the ideas better with slides, I'm not going to do this here, but I want to give a hint of what I used to make this live coding really, that really helped me in the live coding. And that was to ensure correctness. I, of course, write unit tests. So I have a set here of unit tests on the top right of the things that I really wanted to, that the framework should be able to do at the end of the presentation. And of course, I want this to compile and run even if my implementation of the logger is just this. So to do this, I end up with some kind of boilerplate, which and we have to fill in something, if this feature is available, you do the first branch, and if it's not available, you just fail the test. So in C++20, there's a really nice way to write this. You can say if const expr requires, if the provided logger has the trace method available, you can do the trace and verify the results. If not, then you just fail the test. So this is certainly not something new for C++20. This is a well-known pattern. Actually, the auto already revealed that this is a template. So as I understand it, because the template is instantiated by your compiler, it's not necessary that all the code inside of it actually would compile in a standalone setting. So that's the substitution failure is not an error pattern, which is now quite a lot abbreviated because of the use of auto and the const expr requires. So I thought that was a really nice pattern, which I wanted to share with you as well. So I'll leave this out for the remainder of the presentation, just not to clutter the slides too much. But that was a trick I really used and helped me to end up with the right solution at the end of the presentation before. But so logging, I really went down to the basics. My father always told me you have to be a bit lazy, not in the sense that you have to give all the work away to someone else, but to be critical about what you're doing and look for opportunities to do less and achieve the same results. So with that in mind, I set out to find what is the minimum we can log to still get the same results and the same fidelity of logging. So the first is when. So you need some kind of timestamp. You need to know where in the code something was logged. And then finally also there's a what that was logged with additional parameters or arguments and state of that point in the application. So let's start off with a point in time. So what we typically do is just print a timestamp, but come to think of it, and as also mentioned in the keynote this morning, doing calculations with calendars and times and so on, time zones and so can be very difficult and therefore also costly. So if with every line you're logging, you're doing these calculations over and over again, I think that's really a waste. So starting off with C++ Chronos library, you can do, I think, something else which is interesting. So we start off with the high resolution clock, taking the highest accuracy we can get. And let's say we record our time unit in nanoseconds. Then relative to some epoch, we can record the time that has elapsed since then. Then we put this inside a record, which will be our basic unit of logging. So every log statement will correspond to one record further on. So notice that there's no formatting here, so we just query some kind of clock and then store the value. There's no time zone issues, there's no possibility for leap seconds and all the things that can happen with times. And also, we get much more data in a much more compact format. So the thing on the left was already 24 bytes with just millisecond resolution. The solution here with the clock type is only 8 bytes and has nanosecond resolution. So that's really a difference in both formatting and also in verbosity. You will be able to log a lot more of these timestamps relative to printed out text format timestamps. So how do we continue with our logger then? It will be fairly straightforward. We make a template with a trace function, and this trace function will just take this record with the current time and add it to some kind of circular buffer. This circular buffer is also nothing special. It is basically a fixed capacity array, which I mentioned here on the bottom. Fixed allocation, fixed capacity, and heap stack allocated, because we want to avoid any memory expenses. It's allocated before your critical part, which you want to instrument and which you want to measure. So therefore, having reallocations or anything which happen at a fairly unpredictable rate is really not beneficial for the accuracy of the results. There's also here a dimension of the size, so it's fixed, and I chose it to be a power of 2 just to get rid of a modulo operation which you would have to guarantee the circular part of the buffer. And then we have an append method, which is basically a copy of this record into the buffer. So there's no formatting there. It's just taking the binary data of the record and putting it inside of the buffer. With that, we can have a look at our first unit test, which basically instantiates this logger, does a trace, then a sleep, or anything else which would be relevant to measure in time. And then you can add another trace. And this is actually the online part of or this represents the online part of your program. So the thing that you really want to optimize for efficiency and make sure that all the sources of overhead are not disturbing that. Because this is a unit test, it's all in the same method, but that's the distinction we have to make between the online and the offline part. So then we can collect this data from the logger and verify that there are 2 records in there, and we can do any calculations we want based on the time difference between the 2 log statements. So that already gives us in almost system an 8-byte integer, the timing information, which is a good start. The second part, the where, is a little more involved, but we will go through it step by step. And it all started the first time I opened a debugger, put a breakpoint, and then the debugger stops, and it tells you exactly you're now in this file at this line in this method. And I thought, wait, I didn't tell you, I didn't tell that, I didn't program any of that in my source code, so how does it know that? So it's already, it knows where you are, it knows all the details. So actually, why would you add another, or use any means to add the function name into your program? The debugger already knows it. So even though we have in the source location in now, or the preprocessor macros, why would you add additional strings to your program? That was really something that was puzzling me. Also, in general, I think we should be cautious when logging strings. If you can convey the same information with just an integer or an enum or some other data type that is more compact than a string, that's certainly something that could be preferred. So how does the debugger knows it? Well, that's because he has access to the address, the instruction pointer, which is on 64 bits, is of course 8 bytes. And by using the debug information, that is part of a debug build, by default you will be able to resolve this address back to the name of the function, the file, and the line. So all this kind of information is automatically encoded in the debug information. So what should we do now? Should we just include debug information with all our builds? Or also the release builds? Certainly not. So there we can follow the workflow that is typically used in crash dump analysis. So let's have a small intermezzo there. So in that scenario, you have your normal program, you attribute it with a crash handler, which in case something goes wrong, will do necessary things to collect information. So on top of that, also in our release builds, we will add the debug information, which can be quite large, and that's why we are not going to ship that. Seeing a factor 10 increase in program size, or binary size, is not uncommon, so that's really something we don't want to ship with our products. But there's also some more reasons, because if you would share this information, that's actually a risk for people that have other plans with your software. Because if you can locate a certain proprietary code or anything using the debug information, that makes it really much more easy to reverse engineer your software. Also, if you give away the location of some kind of software check or security check, that's also making it really straightforward for someone, for an adversary to know where to look to sabotage it. So no, instead we're going to keep this debug information within the company, make a good archive of that because we will really need it later. So if at a customer a crash happens, it's not always easy to reproduce it. So it's invaluable to have a crash dump. Most of the time with production machines, they will just reboot the machine and start producing again because, well, it's a production environment. You need to create a product. So it's really invaluable to have crash dumps. So what we do is the crash handler will write a file which contains all the necessary information to analyze what happened at this crash. So, and then combining this with the symbol archive, we can translate the addresses which don't mention anything in the crash dump itself, and can be translated back to a full call stack with function names and so on. Something a developer really needs, of course, needs to evaluate what went wrong. So I think there's a lot to learn here, and we can certainly use some of the things in our logging framework. So we'll keep most of it. And as mentioned before, the debugger knows all this information because it's based on the instruction pointer. So what if instead of logging file, function, line, and so on, instead we just write instruction pointers? That was the idea I set out to work on this, and I try to make this work. So these instruction pointers are quite small. So yeah, and these afterwards, if you receive the log file from the customer, you can again use the symbol archive and the symbol information to translate it back into files, lines, and so on. So this minimal log, as I have called it, is very efficient in terms of space. It's not a repeated string over and over again. It's just a minimal information, I think. That's why this presentation is called minimal logging. And it also avoids some of the risks that are typically present if you use normal text, plain text logging. And they are also similar to what we had with the debug information. There's an intellectual risk. If you give away too much of the details of your software in a log file, someone with enough time and enough knowledge can try to reverse engineer and see what is going on there. So that's really something you want to avoid. And also, if you would have a developer which writes a really useful debugging line stating very clearly what is wrong and what the results should be, this might also give away some of the details which you don't want. So by keeping all this information based on symbols which remain inside of your company, you can really protect against that. So with these instruction pointers alone, there's not much you can do unless you start looking at the assembly, of course. So this seems to be promising. Let's have a look what we can do to retrieve this instruction pointer. And what type are we going to give that? Well, it's just another pointer. So we can use the unsigned int pointer type for that, which is is useful because it matches your platform. So 32-bit or 64-bit, it doesn't matter. It will be the correct type. So this makes it easy to write. And then to get the instruction pointer, actually, that's a register in your CPU. It's used all the time by the CPU, so it's readily available and it can be accessed quite quickly. So it requires some inline assembly, which is dependent on the architecture you're working on, but all in all, it might look scary, but it's just copying the data from a register that is already accessed quite frequently into a variable and then returning this. Compare this to retrieving some string which is located in a totally different part of your binary. It's a difference in magnitude, I think. There's only one problem here with this approach, and that is if you do it that way, you will get an instruction pointer which is inside the instruction pointer function, of course. So that's not too helpful if you want to determine where this function was called. So there starts our dance with the compiler to convince it to do the correct inlining and so on. So if we attribute it with an always inline in production code, we will be guaranteed, or it's very likely that this will be inlined and that we will get an instruction pointer at the location where this method is called. This might seem a bit odd, but you can compare it to the source location current, where your compiler also already had to do some tricks to make sure that this is evaluated at the correct site, because it's doing something in a method and it has to know where it was called, so that's already something special as well. In the first try, I used the compiler extension or the compiler method built-in return address, but that is not the thing we want, because that tells you where the code will return to after the function and not where it came from. So in that sense, in some cases you would end up with a wrong address. So how do we add this instruction pointer? We can just take our record and add it in there. It's fairly easy to do that. And then our trace method just gets extended to not only query the current time, but also take the instruction pointer at that point. And of course, here we again have the same issue. If we do it like that, we will always get the instruction pointer in the trace method, which is not ideal, so we have to do another request to the compiler to inline it. So with that, you can see that the second unit test already succeeded or passed, and let's have a look at that test. So we instantiate again a logger. We call this trace method, and there ends our online part. Afterwards, we can collect the data again and verify that it is nothing more than just the size of our time representation and the size of our instruction pointer. So in most cases, this will just be 16 bytes. And with that, feeding it into our model, which is aware of the symbol archive, we can actually query or check that the records in there are valid and that the function name resolves to the name of the test function in this case. So even with this limited amount of data, using the symbols, we can retrieve all the necessary information. This also includes, of course, the line and the number, the line and the function, no, the line and the file, which is also, of course, can be derived by the instruction pointer. So that's our second unit test. Let's have a look at the third one, where we have an example of a simple nested case, where we have a first function that does a trace, then calls a second function, which itself also adds a trace point, and then we return and do the second trace in the first function. So the data that will come out of this is again just 3 times some representation of time and instruction pointer. And if we look at the results, if we would resolve it again in the same fashion as before, we get not the correct results. And that is again another case where we have to convince the compiler not to inline all the things, because, well, the code on the left is so easy that if you turn on any optimizations, it will just inline everything, and yeah, then your test is no longer interesting or doesn't work anymore. So with that, we already know where we have logged anything. Of course, just knowing the location is a good start, but we want to add some state, some more information. So, and with that, we can move on to the third part, the what. And for that, we can just extend the record to include additional arguments. So while we have a record and a trace function, we can easily create a templated record which has an additional argument t here, and make an overload of the trace function, which will also accept an argument. And then in the same fashion, we will just construct a record and dump it to our circular buffer. As I mentioned before, you can't use this with any type. Of course, if you pass it a string, it will just log the pointer, which points to the string. It will not copy the contents, of course. So that's a limitation, but I think, as mentioned before, we should think twice before logging strings. Another clear advantage of this is that this is binary data. So if you log a double to this in this way, you will get the full double precision. There's no data loss there. A while ago, I did some tests and printed out the results with insufficient accuracy. Then I had to redo the entire test just after changing the format to include more digits in my end results. So that was really embarrassing. So that's something that can also be avoided here by just using the binary data. And then you could actually do the formatting offline, separate from the logging and independent of that. So, but now we get a data stream in our logger, which can vary depending on the arguments that are logged. So what is still missing is a way to identify the type of argument that was logged. And there are several ways you could go about this. You could use some kind of name mangling scheme or some kind of structure which encodes this information. But I think I found a quite nifty way of doing this. And to get there, we have to realize that actually this trace method consists of two parts. That's being the instruction, getting the instruction pointer. That's why we inline this method. And the remainder, which just adds the record to the circular buffer. So because this gets inlined, there's no mention of the trace function, so we lose all the information of the template that was present here. So instead we can split it up in two parts. So we have a outer trace function which just does the instruction pointer bit and gets inlined so that it's really the call side of this trace function. And then we can add a second part, a trace inner method, which is not inlined and where we do the remainder. Of course, this alone doesn't change anything, but what we can do now, and that's one of the main tricks here, is we can call this instruction pointer method again, because once we get into this bottom function, this trace inner, we still know the type information of the template that was passed there. So if we will be resolving this second instruction pointer, we will be able to see, okay, this was a trace call which was called with a boolean. This was called with an integer, with an unsigned integer. That's still wrong. That's another surprise I came across during this adventure. And for that, we have to realize that this circular buffer append is nothing more than just copying data. So if we look at this boolean, that will be a record T which has 1 byte for the argument, and the integer and unsigned integer will actually be both the same 8 bytes for this data type. So our clever compiler just saw unsigned int or int. It doesn't matter for me. The implementation and the remainder of what is done in this append method is irrelevant. I will just reuse that. So that's why we get twice resolve this to trace inner int instead of unsigned. So to counter that, we're back to our dance with the compiler. We have to ask it politely to not reuse the implementation of this function. This really increased my ow for the compiler, because I didn't expect the compiler to do that. So by adding this used statement, we correctly resolve the third one to be a trace call, which was done with an unsigned integer. So, and that's actually the hardest part of this talk. With that, we actually fix all but one of our unit tests. The last one is about multiple arguments. So what we can do there is of course the variadic template extension, and extend our record T with something that looks like a tuple, and add some S's and some dots in the correct places to end up with a variadic template which can take an arbitrary amount of arguments. The remainder of the code is the same. We still use a second instruction pointer to encode the data or the types of the data that were logged. And all in all, it's just pushing this data into the circular buffer. It's really interesting to see the resulting assembly. If you look at this after the compiler optimized it, because all these abstractions with the record and the tuple and so on, this all gets abstracted away or optimized away, and it's really nice code. It's taking the clock, copying it, taking some instruction pointers and copying it. There's in no case this record T is actually instantiated as such. So also from a memory point of view, it's really efficient. So with that, we can actually already summarize what I've called minimal logging. So we've split logging up into two parts, being the online part where we want to have a very performant logging framework which does not include any of the formatting overhead, is very condensed, so you can pack a lot of information into a single log file, and is also really memory efficient. And an offline part where we can do all the more expensive parts of the processing. So we did this by creating a circular buffer, which in itself just contains an integer representing the time, an unsigned integer representing the location where the trace call was done, and then also a second instruction pointer in the function in this trace inner function, which we will need later. This is then followed by one or more arguments, which are just in binary data after your circular, after the other data. So once you're out of your performance critical part of the code, you could write this circular buffer to a file and do an offline analysis with that. So in there you can decode this data again to include actual timestamps in the time zones and all the information and detail you want. You can use the symbol information to retrieve the file, line, and function using the symbol information. We can also get back the types of the arguments that were passed to the trace function. And with that, we can decode the optional arguments. So this actually already gives us all the information to write, again, a full text log. But I think we should move on from purely text-based logging to something else, because once you have this in a model, you can present it in a much more advanced way in some kind of viewer where you can do filtering, where you can change the formatting and so on. So there's a lot of opportunities there to work with the log files in a much easier way than having to decode text-based log files. And with that, we're through the slides. So if there's any questions, I'll happily try to answer them. There's some bonus material if we have time that I can go through, but I'll first open it for questions.
So the question is, how do you evolve viewer, and like how do you deal with old logs? I understand that you have a set of types you support decoding, which are like primitive types. You never extend them with your, like custom structures or something like this, because I understand. So when you get this like function pointer to the actual implementation, do you like take a function string and from there you get template parameter of a type that is actually decoded, and then you do the string rendering? Or so that like my point is like, how do you evolve this? So let's say you add new structure to log, and then it was not present in previous format, or like vice versa. Like how does it happen?
From the online part, it doesn't change anything. But indeed, if you add custom types to your logging, you will have to implement it also in the what I called here the log model to be able to decode and do the interpretation of that data indeed. So
and second thing, did you look at the projects like SPD log, which are doing the logging outside of hot path through, well, they use also shared memory, just memory queue, but do it in a second, in a logger thread, just offloading it from a hot path from the.
Yes, I saw that, but I really wanted to focus on this instruction pointer and see with what was the fewest amount of information we could log to still be able to retrieve all the details. So.
And the last question. So couldn't you use the variant and use 1 byte to encode type instead of function pointer of 8 bytes for the, just take the type index from a list to encode it, which argument is supplied, stuff like this.
That's also a possibility, but I wanted to have something which was really independent of the number of arguments.
Right, yeah.
And that's why I
right. Yeah.
It's indeed 8 bytes to determine if it's an integer or a bool is perhaps a lot, but it extends quite nicely if you have more arguments or more types. But good question, thank you.
Yes, thanks for the talk. First question, do you have published a library somewhere where?
Not yet, no. I'm planning on doing that, but there's some other things at home that with a recent daughter. But yeah, that's surely a plan. So if you're interested in that, please drop me a line and I will notify you when this is available in GitHub or anything. Yeah.
Okay, second question is going a bit deeper. If you use the instruction pointer, are you not getting trouble with address randomization? So if your binary is loaded by the operating system, it will get a random address, and I would guess the instruction pointer will only give you the random address, which is not enough to decipher the debug information, I guess.
Yes, actually you need to load, indeed need to know the load address of your binaries. So you also have to, I didn't mention this here because this goes perhaps in too much detail, but you also need to know the relative address to where you were loaded. This is the same if you would want to support shared libraries and so on. For each of the binaries, you need to know the load address because also the symbol information is always relative to the load address. So that's some additional information, of course, you need. But as this is mostly bookkeeping, I try to minimize this in this talk. But indeed, that's surely the case. Thank you.
Thank you for the talk. It's very clever. I notice when you call the get instruction pointer a second time to indirectly get the kinds of arguments that you're logging, have you experimented with instead passing in the address of the trace in a member function that you're calling?
I have not. That's a good idea. That's something I could try, yeah.
Thank you.
Yeah, hi. Thanks for your talk. It was very informative. You showed the timings in the beginning, and I was wondering, have you considered the effects of logging to file versus logging to standard out versus maybe just logging to some UI widget in there, or do you know how much of it would affect there?
That's a good question, and that's the reason I didn't put any numbers on that slide. I just wanted to give some hand-waving idea of the scale of things and the amount of time that is taken by some of the logging. But indeed, writing to a file or writing to a standard out might give different results, but that's something...
And the second point that I had was you were now trying to remove, as you put on your slide, trying to remove all the verbosity from your logs. You might have in an application like industrial machining, you want to show some kind of log information also to a user on screen or in a command line output. I don't know, object XY is broken, please replace, or whatever. Would you split this then off into a separate logging mechanism, or how would this interfere or not interfere with this? Because I guess, yes, for debug logs, this makes a whole lot of sense, but for user logs, you want to keep the verbosity to kind of tell them what's there.
Yes, this is really intended for logging, which only is relevant for developers. So if you want, you still need to provide sufficient feedback, of course, for your operators, so that they don't, that they still know what is going on. Because that's indeed. Then I would split it up in user logging and developer logging, and handle these separately. So even though the user logging might then be slightly slower, or it might still give sufficient feedback. Yeah, indeed.
Okay, thanks.
Thank you.
Hi. So I had a question regarding the inline and no inline attributes that we used. So if I understood it correctly, if I understand it correctly, the compiler can just like choose to ignore those as well and do inlining when it shouldn't, and not do inlining when we ask it to. So do you have any strategies to at least like detect that, or how to handle that? Because we might not notice it when we are compiling the code, and much later when we see the logs, it might become a bit like
Yeah,
difficult.
That's a very good point indeed. You ask the compiler politely to do this, but it's not guaranteed. That's why I have unit tests, because I run them with the same compiler in the same environment as my production code would be, and there I didn't detect any of these things. But
so then you'll have to write unit test for this for every function you are trying to use it for, right? Because the unit test might work for this function, the one you wrote in the unit test, but in the real world, the production code, that part might be inlined or not inlined, right?
Yeah, that's true. But then again, if you're logging in something that gets inlined, perhaps, yeah, indeed, that's a fair point. It's something. It would be nice if we could detect that, or at least get a warning if the compiler didn't inline it, even though we asked.
And on the same note, so we are telling the compiler to not inline something, which might affect performance as well, right?
Yes.
Okay. But then we have to kind of be just aware of that.
I asked it not to inline in the unit test, just to get with the nested functions, just to get a simple example. You wouldn't do this in production.
Because in production code, then you'll have to use no inline everywhere, right? Wherever you want to measure this. Because otherwise, if it inlined that function, then your instructor pointer would be just pointing to a wrong
different function. Yes, indeed.
So essentially, every line, like everything you need in your code now, will need to be no inline.
Right, unoptimized.
Unoptimized, essentially, which is
That's not ideal, indeed.
Okay.
That's a good point. I should think about how we can. Yeah.
Okay. Cool.
Thank you.
Thank you.
Yeah, actually my question was very similar. So I did something similar before also, and in my experience, the aggressive inlining makes a problem there. So from what I understood is you just log the information, there is a bool, and it's like true, and it's crucial to find the code place to make sense out of it, right?
Yeah.
And so when the compiler is inlining actually this function which is logging, then you will get it just somewhere else. So
and even multiple things on the same line.
So the optimization basically spoils it a bit. So as he said, you would have to make it only sensible in an unoptimized build, and that's not production.
Yeah, that's something in a bigger context I didn't think about yet, or I have no sufficient experience with yet. So that's
Okay, thank you.
Maybe there's still time to show some of my bonus slides. There's one nice advantage of having of doing this logging this way is if we have to look back at the crash dump workflow, because the crash dump already contains your stack to be able to reproduce the call stack. By walking the stack frames, it actually also contains the log up to that crash. So from your crash dump, you can, with some tricks, retrieve the circular buffer which was used to store the logging information. So with that, you could end up with the exact logging which is present up to that point. So that's a nice thing. Also, what I thought about for future extensions is working with literals, because if your program is full of logging fixed strings, there's no point in doing that. It's just wasting space. So if there would be a way to detect these literals, you could actually not log them, and then have tooling which in the offline phase just re-adds them and adds the literals again. So that way you can save in the log size by not logging the things which are just clearly present in the code and don't need to be logged. The third slide I still have here is about shared libraries. So that was the question before. Symbols are always relative to the load address, so you can. That's also something that you have to take into account, and you can just use the load address to figure out these things. And that's the same way as crash dumps do it. They just store the load address for each of the binaries, so it can be determined, okay, this instruction pointer is in this range, so it belongs to this binary. And then the last thing I'm going to mention is that this way of logging also gives you information about the version of your software. This can be done in the same way again as crash dumps. There you also store some kind of build ID of your binaries. So because this is used for storing your symbols and matching those, you can also again find out which version of your software was used for the logging. Now it's sometimes difficult to find out, especially if machines are running for a very long time, to find which version was this again. So that's also an advantage, because the symbols have to match the log file. You can that way also determine which version this was. So that's based on this build ID, which is built in. Okay. With that, I'd like to thank you for coming to my talk, and I hope you have a great conference. Thank you.